Hello, this is John Wayne. The title of the talk is on machine thinking. In 2020, at International Conference on Developmental Learning, I proposed conscious learning through lifelong APFGP for autonomous programming for general purposes. In other words, the learning process must be conscious. Outline, I will talk about introduction, the first theory of machine thinking, developmental network tool, experiments, and conclusion discussions. AI is a crisis. Since 2015, all AI papers in Nature are flawed. I sent a letter to Nature, available at my website. And why the AI is in crisis? Because we do not want to see the details of theories. Alan Turing in 1950 asked a very important question: can machines think? In the same article, he said, I believe that at the end of this century, the use of words and a general educated opinion will have altered so much that one will be able to speak of machine thinking without expecting to be contradicted. However, the existing studies about machine thinking are without definition of machine thinking. Why we have this situation? Because understanding brain is a great challenge, and brain is like an elephant. Disciplines like biology, neuroscience, psychology, electrical engineering, computer science, mathematics, and also physics. Each discipline is like a brain man. We motivate our definition in terms of human brain has to be general purpose. And our definition is also take into account lifelong learning from infancy to adulthood. Turing machine is a tape and it has a read-write head and a controller. And it's good because the head can scan, it's like attention. Read means sensing, write means action, and the state is a context. It uses symbols and does not have internal representation. But a tool is very useful for us to understand that Turing machine is a mapping from state and a tape symbol to the next state, next text symbol, and direction of the read-write head. Turing machine is basically a lookup table as a transition. As I said earlier, it's a 5 tuple from 2 to 3. Universal Turing machine is a very important power for Turing machine. Input tape has 2 parts. One is a program encoded and the data for the program to apply to. Because the user can write any programs, then the universal Turing machine is general purpose. That's the basic model based on which we have general purpose computers. You can see that they have a 5 tuple, 1, 2, 3, 4, 5. The UTM, universal Turing machine, simulates the program and the data, output the result to the tape. The control of a Turing machine is a FA, and all you need is just redefine the mapping, extended the state space so that the output, the state, and also the actions, then it becomes like finite state lookup table. Developmental network, short for DM, it's not symbolic. Although we have a symbolic network, the alpha, beta, gamma, those are the states, then the transition. It has a feature input, but feature input is converting the symbol, so become ABC. And those are the state-to-state transition with input. Over here, the state is emerging, right, in Z area, and the input is directly image, and not just the symbol. but rather the entire image. Each neuron in the hidden area can attend to the global images or a part of images. So which neuron wins through competition, then the winning neuron will attend to the global view or local view of the location or different patch. And each neuron will have top-down input that match the state and bottom-up input with attended input. So you can see that each neuron corresponding to an entry in the lookup table of the final state machine. And over here you have computation, which neuron fires. You will use Hebbian learning to link to the next state or action, Z. And learning is created and updated in real time on the fly. Over here is winning neuron is looking at the global view. And over here, the winning neuron is looking at the local view. So the attention is automatic and through competition in the hidden area. Let's look at how developmental networks work in the real world. We want to for the time because networks are highly recurrent. They are top-down, bottom-up, and extremely difficult to understand. We have a sensible word, WX. We have an actable word, WZ. Then the sensory X will take image from sensible word, and the actable word can be taught to motor Z through supervised learning or self-supervised learning or reinforced learning. Then the skull-closed brain is Y. So we define XYZ as a context, and unfolding through time, then the network, all you need to just establish mapping between the context. It becomes a very interesting engineering and mathematical problem is to establish the mapping of context 0, 1, 2, and 3. We need a GNSMA, which is 8 properties. G for grounded, E for emergent, M for natural, I for incremental, S for skull closed, attentive, motivated, abstract. And for planning, we need to have a covert action and overt action, and each motor component corresponding to one motor that's a covert, and in biology, it's in the pre-motor area, and overt motor. Definition of thinking, animal-like thinking must be general, learned, we are sensory motor, higher concepts emerging. And then we have a covert part, we have a displayable part, which is overt, and it's fully autonomous, whether you want to be covert or overt. And here's an example abstraction, because just detailed motor is not very powerful for complexity issues. And we're here, we have where, what, concept, which, when, and why. And that in the experiment, we talk about corresponding to the navigation example. Theorem 1, multi-stage abstraction. We have n Super-Turing machines, and over here, n, suppose we need to go through this sequence. Each Super-Turing machine has a k transactions, 1 through k. Number 2 transaction in this case is k to the m. And with abstraction, we need to only teach k times n sequences because all the states will collapse. That's power for abstraction. Context chaining, a chain of brain activities that includes covert thoughts and overt displays of actions, is a chaining of element Super-Turing machines based on activated context as a result of competition among learned contexts. Theorem 2, winning context. Each time t, you have multiple k Super-Turing machines available with q as its initial state. Many Turing machines compete, and concepts taught before t influence what context q wins at time t. Grand emerging universal Turing machine, here I'll give you an example. You have a forward motion skill, right turn, left turn, avoid obstacle, learning route 1 with corresponding cost, distance, learning route 2 with corresponding cost, learn how to compare the cost, and then over here you learn, you have multiple plan, which plan to choose depends on the cost. And this is the experiment we use as an example of planning. Developmental networks, look at the DN1 first, because simpler, you have 3 areas, X, Y, Z. When time runs forever, then you have each neuron has a bottom-up and top-down input, and the neuron network is updated to prime with response. Unified bottom-up input match with the bottom-up weight, top-down input match with the top-down weight. Then you have inner product V dot P. Then you do computation, find a max match. Theorem DM said control of a Turing machine is a finite state machine, FA, finite automata. DN's emergent control of a Turing machine, and DN is optimal in learning any Turing machine and a sufficient neurons. If you do have sufficient neurons and the DN is error-free, no error at all, because you use each neuron to remember each transition. You don't have enough neurons because the new word, you have infinite many inputs and infinite motors, then it's optimal in the maximum likelihood. Emergent Turing machine is logically complete and like a universal Turing machine. Emergent Turing machine with motivation automatically self-programs with motivation. But in this talk, I will not talk about motivation. And DN2 is a later version of DN1. Each neuron has its own computation zone. The computation zone is learned by dedicated inhibitory neuron. A neuron file, if its pre-action potential is among the top K in the computation zone. Why each neuron needs its own computation zone? Because we want to automatically generate a hidden hierarchy. Here is the learning procedure, and each neuron in Z has a high-level concept, low-level concept, and the input, you have a grid mark, GPS, image of the vision, and the hidden neuron, you have a connection patterns, X, Y, Z, and 0 means do not connect, 1 means connected. So the hidden neuron has different connection pattern to start with. Here in DA2 algorithm, you have a context, use memory, and after the memory of the area function Y, you update your memory and you update your response. And that's for Y, and Z doing the same thing. So the area function are basically the same between hidden area and motor area. Experiment, we motivate our experiment by experimentally realize the model of thinking. We want to measure the performance of DN2 learning thinking through scaffolding, which means earlier learned simple skills facilitate later learning of complex skills. And we teach rules that's not in the program, but rather in the mind of the teacher. For the GPS concepts, turn open grid if there is obstacles. If a traffic light is red, you stop until it turns into green, keep track of distance, and go back to reach the destination. And the Z concept have a lower concept and a higher concept, as we said earlier. And this is a graph user interface that user can use to teach at the end, where you have obstacles, you have traffic signals, and you have pixels that looks at front. And these are the detection lines, and they give you the distance, and GPS give you the directions to go, but the obstacle may block your direction. Over here, we have basic skills taught at different settings, then it tested on new settings. Each setting, you have multiple routes. The solid lines are chosen plain, dashed line has higher cost, was not picked up. Performance of new setting for 1 to 3, 100%, no error, and success rate is 100%. So in other words, it's very robust. So let's do a conclusion and discussions. Thinking as a necessary condition for conscious learning, published ICDL 2020. Thinking as a DN2 numerical computations. Learned skills successfully applied to new maze settings. Thank you very much.